Welcome to part 3 of MOSFET's fundamentals. In this video, I'm going to talk about saturation mode. In most cases, whenever we bias transistors, especially MOSFETs, we bias them in saturation modes as opposed to BJTs. As the value of VGS changes with respect to the value of VDS, the slope of this channel changes. At some point, the slope will completely close up and then not allow electrons to flow from here to there through the channel. But then that doesn't mean that electrons will stop flowing. Electrons will continue flowing, but now they won't be controlled because we know that the voltage, the current that was here was controlled by Vg and VDS. Now there's just going to be like a flow of current in directly into this channel without any control. Okay. Now from here, we do like that state because it actually gives us some interesting characteristics. When the transistor is in saturation, now the relationship between VGS and ID is defined by this equation. When it's not in saturation, when it's in triode mode, which was discussed in the second video, it's defined by this equation. In saturation mode, just like explained in part 2 of the video, when VDS changes, ID does not change. But in saturation mode, only VGS can change ID. The relationship between ID and VGS is shown in this graph. So, let's say now we have current, we have VGS. Assuming that VDS is somewhere up here, meaning we have some specific VDS up here. When we increase I'm talking in terms of voltage because this graph doesn't show VDS, but then assuming that I'm talking about the relation, the difference between VGS and VDS. Okay, so we know that VGS must be VTN more than VDS for this transistor to be in the triode mode. Okay, so now let's look at what's going to happen. As VDS increases from 0, the transistor is in cut-off mode, meaning it has not overcome the VTN. VTN is a threshold voltage that we need to power the transistor. So the transistor is not powered yet. Now, we are at this point. Now, when we move from here to this point, we hit what we call the saturation mode. We hit saturation because VGS and VTN are less than VDS, meaning VDS is less than VGS plus VTN, and that mode is called saturation mode. We say a transistor is in saturation is if VDS is more than VGS plus VTN, but if VGS plus VTN is less than VDS, the transistor is in saturation. Just like shown in the previous graph, as VGS increases, it hits saturation first before it hits the triode mode. So the voltage will move until it reaches a specific point. Now, from that point, it will be in the triode mode. Okay, but then I want us to focus on the state where the transistor is in saturation mode. We want to keep the transistor biased in this region for us to be able to do some really cool stuff that I'm going to talk about in the next coming videos. But let's look at this. If, assuming that there is a small change in VGS, looking at the slope over here, let me get this straight, the slope over here. Assuming that there is a small change in VGS, let's say VGS is here, and there is a small change in VGS, with a small change in VGS, you can map out specific changes in ID. But then here, you can see that with a small change in VGS, we can be able to induce a huge change of current in our drain. This current is flowing down our drain. If you look at the line that connects this, we know for a fact because of our relationship equation that this line is not linear, it's exponential. But if VGS changes and if VGS becomes very small, that means if the gradient or the derivative of VGS with respect to the transistor is very small, ID will change drastically, and then the slope that relates these two equations looks almost linear, and we can approximate this and say it's linear. We call this slope transconductance. And this transconductance is equal to the change of IDQ with a small IDQ, which is basically our AC or alternating current IDQ, going up and going down, changing this current there, and also changing this voltage here by supplying an input voltage there, which shakes this bias point, will actually give us a linear relationship here. So, in saturation, going through the notes then, ID does not change with respect to VDS. That means ID remains constant. And the only change in ID depends on VG, meaning, okay, now it gives us like an advantage of being able to actually change and do stuff with the transistor without like looking at a lot of variables. Because if it's in triode mode, it's hard to control because like the change is not linear. So we do know for a fact that like what we actually want when we bias transistors, we want to bias them in a linear region so that we can be able to control linear parameters like gain and like a current gain and impedance. So for those things to be able to be related like linearly, we need to bias this in a linear region. So this is not completely linear, but like the relationship is linear. So the relationship between VGS and IDQ. So we can already get a sense that if we have to actually like apply an input somewhere, we're going to apply the input at VGS. Well, for MOSFET, there can be other configurations which like this thing can be connected in, which like will be looked at later as well. But then like in this video, we're gonna be talking about I mean like we are only focusing on this part of the like this part, so where only VGS changes. So going to the second point, assuming VGS is varied by an input voltage, when VGS changes, it changes ID exponentially. Now, the scale of change in like in the ID with respect to VGS means basically this scaling here depends on Kn. Kn is a physical is a physical parameter which is controlled by the design. Basically, it depends on the width and the length of the transistor. The gate, sorry, not the transistor. It depends on the length and the width of the gate of the transistor. So finally, I can say that like something very important about saturation to keep with you is that in saturation, as VGS changes, like ID changes exponentially, but when there's a small change in VGS, it actually approximates to a linear change in ID as well. So you can actually look at this as if it's a linear change. Right, so there is almost a linear change here, and that is exactly why we approximate that the change in ID when VDS changes, when this thing is in saturation, is constant when VDS is constant. Okay, so let's leave it here. In the next video, I'm going to be explaining the relationship between this graph, which is basically like the features of a transistor, and us having a circuit. Okay, thank you.